All right, today we're going to jump right into the world of matrix algebra. This stuff is a huge deal in math and computer science. So we're going to break down what a matrix is and learn the basic operations that make them so incredibly useful. So, to get started, I want you to think about numbers in, well, a totally new way. Usually, we just see a 5 or a 10 all by itself. But what if numbers could be arranged in a grid? Like a formation. Think of a marching band or the layout of a city block. And that formation, that's a matrix. It's just a grid of numbers. And the really cool part? This grid plays by its own special set of rules for math. Rules that are a little different from what we're used to with single numbers. Okay, so first things first. What is a matrix really? Well, it all boils down to two simple ideas, rows and columns. Yeah, I know, here's the textbook definition, but trust me, it's super simple. A matrix is just a rectangle, a grid, packed with numbers that are all organized neatly. If you can picture a spreadsheet, you're pretty much there. Now, when we talk about the size of a matrix, we call those its dimensions. And here's the key. It's always rows first, then columns. Always. So this guy right here has 2 rows and 3 columns, which makes it a 2 by 3 matrix. Easy, right? And just like coordinates on a map, every single number inside has a specific address. If you want to find one, you use its IJ entry. The I tells you the row number, and the J tells you the column number. So in this example, the 2-3 entry is 6, because it's in the second row, third column. All right, we know what they are, we know how to read them, now let's actually do something with them. First up, let's learn how to add these grids of numbers together. So before I just give you the answer, take a look at these two. If I asked you to add them together, what would your gut tell you to do? Seriously, how would you guess it works? Because chances are, you're probably right. Hold on though. Before we do anything, there is one non-negotiable rule. You can only add matrices if they are the exact same size. Their dimensions have to match up perfectly. You can't add a 2 by 3 to a 2 by 2, it just doesn't work. And see, the process is exactly what you thought it would be. It's super intuitive. You just add the numbers that are in the exact same spot, top left with top left, bottom right with bottom right, and so on for every position. The answer is a brand new matrix that's the exact same size as the ones you started with. And here's the best part. You don't have to throw out all the math rules you already know. Just like 5 plus 3 is the same as 3 plus 5, the order doesn't matter here either. Matrix A plus matrix B, it's the exact same thing as B plus A. That's called the commutative law, and it keeps things nice and predictable. Okay, we've done addition. Next up, what if we want to make every number inside a matrix bigger or smaller, all at once? Well, that's where scaling comes in. The fancy term for this is scalar multiplication. And that word scalar, it's just a cool name for a single, regular number, not a whole matrix. All we're doing is taking that one number and multiplying it by every single thing inside the matrix. And actually doing it couldn't be easier. You want to find 5 times a matrix? You literally just multiply every single entry inside that matrix by 5. The scalar just gets shared with the whole grid. That's it. So what about the number 1? Well, you guessed it, it works just like it always does. It's what we call the multiplicative identity. Any matrix times 1 is just the same matrix back again, no changes. Okay, this next move is a little different. It's not about adding or multiplying. It's about physically reorienting the matrix itself. We're going to learn how to flip the grid. This flip is called the transpose, and we show it with a little superscript T. The idea is really simple. The first column of your original matrix becomes the first row of the new one. The second column becomes the second row, and you just keep going like that until you're done. Now, to really picture this, the trick is to find what's called the main diagonal. That's the line of numbers that goes from the top left corner down towards the right. Think of that line as a hinge, an axis that we're going to flip everything across. And bam, there you have it. You can see the numbers on that main diagonal. They stay right where they are. Everything else just flips over to the other side. And notice this, the dimensions totally swap. A 3 by 2 matrix flips into a 2 by 3. Okay, so we've got addition, scaling, and flipping down. Now let's talk about the rulebook, the official guide that makes all of this work so predictably. You know, the best thing about all this is that it's not chaotic or random. There's a solid, logical set of rules, and a lot of them are going to feel really familiar, kind of like the math you've been doing for years. So here's a quick look at the greatest hits. We've got the commutative law for addition, That's the A plus B equals B plus A thing we talked about. And then you've got associative and distributive laws. Basically, it all just means you can move things around and group them in common sense ways, just like you'd expect. So why do we even care about all these formal rules? What's the point? Well, here it is. These rules are what let us treat a whole grid of numbers, this entire matrix, as if it's just one thing, like a single variable, an x or a y. And that is what makes solving insanely complex problems possible, like rendering 3D graphics in a video game or tackling a system with hundreds of equations at once. So there you have it. The basics are under our belt. We can add them, scale them, and flip them. But the real adventure, the thing that truly unleashes their power, begins when we ask a new question. What happens when you multiply one matrix by another matrix? Now that's a whole other level, and it's where the real power begins. But it's also a topic for another explainer.